Okay, for this one, I'm going to need a graph like this. And then what I'm going to do is I'm going to draw a randomly shaped graph and just call it y is equal to f of x. So let's just draw a random shape like that. And this is going to be y is equal to f of x. Alright, now what I'm going to do is I'm going to mark a random x coordinate. Let's mark it over here and let's just call it x. Alright. And since this is y is equal to f of x, the y coordinate of that would be f of x, right? And then I'm going to go a teeny weeny little bit along the x-axis, and let's just call that distance a. So I'm going to go a distance of a like that, and then the coordinate right here would be x plus a, and then automatically this is going to be f of x plus a, isn't it? Alright, after that, if we are considering this, the area of this little part here as a of x, then automatically the area of this big part would be a of x plus a, and that would be a of x plus a. And if we just consider that this little part here, damn it, sorry, if we consider this little part here, we can get this area by reducing this little area by this total part, and that total part would be a of x plus a, and I'm going to reduce a of x from it, and then we can get the area of this part, right? Now I'm going to separately draw this one over here like so. I'm just going to mark the dimensions of it. The width is a, and this height would be f of x plus a. This height would be f of x. And now, if you're considering the area of this little rectangular part, I can write it as f of x times a, can't I? And you can clearly see the area of that little part is obviously less than the part that we considered. So the area of the part that we considered is this, so its area is greater than what I've just said, that's f of x times a. And also, now we're going to consider this big rectangular part, and that's its area would be f of x plus a times a, wouldn't it? So obviously we can write it like so. Alright, here comes the fun part. Now what I'm going to do is I'm going to divide this whole expression from a, and it would look something like this: a of x plus a minus a of x divided by a is less than or equal to f of x plus a. A is obviously greater than 0. Okay. Now I'm going to set a limit, and the limit would be limit of a as a approaches 0. So limit of a as a approaches 0 across the expression like so. Now if we apply the limit, nothing happens over here, so we can just write it as f of x. And as you can see, this is very interesting. As you can see, if you notice, this is actually the first principle of the derivatives. So this is actually a dash of x, isn't it? And this one, when a is approaching 0, I can write it as f of x. And you do realize now we can write a dash of x is equal to f of x. And this is actually the derivative of the area of the part that we consider. In order to reverse the derivative, what do? We integrate it. So if we integrate this equation with respect to x like so, what do we get? We get a of x is actually equal to integration of f of x respect to x. So that's how you prove that integrating a certain formula or equation gives you the area. Now there's a lot of other ways to prove this one, but I found this method particularly interesting. That's why I wanted to share it with you guys.